So let's take a look at our final set of notes in topic 10, which is all about introducing definite integrals. So we're going to talk about the definition of the definite integral and how it relates to area, and we're also going to see in its definition how it relates to Riemann sums, which we were just discussing in the 10.3 notes. And we're not really going to do anything specifically with definite integral processes yet. That's going to come in topic 11 where we learn the fundamental theorem of calculus and the evaluation method. But what we're going to do is we are going to look at how to calculate basic definite integrals using not only the limit definition of the Riemann sum, but also just basic geometry to again emphasize the fact that this idea of the definite integral relates to this idea of finding the area beneath the curve. So we already did a little bit of calculating basic integrals with geometry in the previous set of notes just before introducing Riemann sums, but now we're going to do it by also linking it to the new notation we're going to learn for definite integrals. So again, we're not going to do any actual definite integral computation yet because we do need the evaluation theorem or the evaluation method from the fundamental theorem of calculus, but we are going to introduce it in a little bit more detail so that we know what to expect when we get to actually calculating these definite integrals with calculus. So let's go back to our Riemann sums. So as we saw in the previous set of notes, the Riemann sum method gives us a way of approximating the area beneath the function of a curve defined on an interval by using a sum of areas of rectangles. So essentially, just to recall the idea, is we take our generic function here that I've got a picture of, we divide the x-axis on the interval from a to b into n regions of equal width. Remember that this gave us the width of our rectangles. And then we used sum method, either using left endpoints, right endpoints, or midpoints to determine the heights of the rectangles. So we chose a point, some x value, on our interval, and we saw where the function hit or where that value of x was on the function, and that gave us the rectangle heights. And so the area of the ith rectangle is given by this idea of the Riemann sum. And so when we talk about the area of all of the rectangles, you can think of it as the area of the approximate area under the function is given by that Riemann sum, the sum of the areas of the rectangles, so the widths times the heights, and we just sum all of those. So how does this give rise to the definition of the definite integral? How do we go from this, which is a very geometric way of assessing area, to the calculus way of assessing area? It has to do with the number of the rectangles that we use. So let's say we have a function f of x continuous on the interval from a to b. In the process of the Riemann sum approximation, the larger we make n, meaning the more rectangles we create, the more precise our approximation gets in terms of the actual specific area of the function. And specifically, if we take the limit as n goes to infinity of our Riemann sum, that is the definition of the definite integral. And the definite integral gives us the precise or exact measurement of the area beneath the curve. Provided, of course, that we can take this limit and it takes the same value for all possible ways we could pick that x star. So, sorry, left endpoints, right endpoints, or midpoints. So this is the link. It all comes down to limits, as it often does. We have this geometric definition, the Riemann sum, which gives us approximate area beneath a curve. But if we take the limit of the Riemann sum, where we let n go to infinity, so essentially we create an infinite number of rectangles, what that gives us is it gives us the exact area under the curve And that exact area is the definite integral. So the Riemann sum, this thing, gives us an approximate area. The definite integral, this thing, gives us the exact area because now we're taking the limit of the Riemann sum as n goes to infinity. And so if we have an infinite number of rectangles, essentially what we've done is we've divided up those rectangles enough so that we can get the exact area under the curve. Now, I want to mention a couple things about the notation for the definite integral. So the notation should look somewhat similar to what we saw in the 10.1 notes. The real difference now is we have these things, this a and this b. So let a and b be the values of the interval that we're interested in. So typically when we talk about integrating, we're integrating to find an area over a region, like from a to b. Then we can express the definite integral, and I'll highlight this because it's an important piece of notation, in this form. And so this thing can be read as the definite integral of the function f of x, from a to b. Now, just a note about this notation, because it's kind of cool. This notation actually is one of the original pieces of notation of calculus. So if you go back to the late 1600s, early 1700s, when Newton and Leibniz were developing calculus independently from one another, Newton in England, Leibniz in Germany, this is one of Leibniz's original notations. It's this elongated S shape to represent that sum, that idea of summing an infinite number of areas. He had this idea of the infinitesimal. It's not quite the same as we understand it now, but it's that basis idea of taking a limit of that Riemann sum idea, which I think that's kind of cool that this notation is still used and has been used since it was first introduced in the 1600s. I think that's cool. Also, if you're interested, one interesting piece of math history to look up is that debate or that controversy about Newton and Leibniz. There was a lot of controversy over who actually came up with calculus first. Was Leibniz plagiarizing from Newton? There was a lot of conflict and a lot of back and forth between the two, or between Leibniz and one of Newton's correspondents. The general consensus today is that they actually did independently come up with the idea of calculus. But it's an interesting piece of math history, and it's my favorite piece of math history, so I get really excited about it. But it's something interesting. So if you're curious, look up the Newton-Leibniz controversy, and you'll see a lot of stuff about early calculus, where it comes from, all sorts of stuff about it. Really interesting stuff. Anyway, get off my little calculus soapbox. Just a couple other things about some phrasings or some definitions involving this particular notation. I've mentioned this word before, but here I'm just putting it as a word in the notes so we see it somewhere. The thing we're integrating, the function we're integrating, is called the integrand. Those values a and b, they're usually called the limits of the integral. And the region from a to b is usually called the interval of integration or the domain of integration. So if you hear those terms, that's what they're referring to. I'll keep using integrand. I'll use limits of the integral quite a bit as well. But that's some of the terminology that we see. Now, we're finally getting into talking about the definite integral, and this is what we're going to see basically for the rest of the semester, the idea of the definite integral. And so I want to talk very briefly about a couple ways of interpreting the meaning of a definite integral depending on the type of function that you have. And this was also something we sort of mentioned when we talked about Riemann sums, but just to bring it up here again. Let's say your function is integrable and it's above the x-axis, so greater than or equal to 0 on a to b. So maybe we have something like this. So here's our little plot. Here's a, here's b, and our function is above the x-axis on that interval. So maybe it looks like this, just kind of a basic shape. So when we talk about the definite integral in this sort of scenario, when our function is completely above the x-axis on the interval of interest, the definite integral can be thought of as draw that in there, the area beneath the curve of the function and the x-axis. So is this area bounded by the function's curve and the x-axis below it? That's one way of interpreting the definite integral if you've got the whole function above the x-axis on the interval of interest. But like we saw actually in that last example with Riemann sums, that's not always the case with functions. So we might have a situation where maybe our function is not always above the x-axis on our interval. So maybe our function looks like this. So we can see it dips below the x-axis there a little bit between a and b. If this is the case, then when we compute the definite integral, you can think of it as a signed measure of area or net area, meaning that areas above the x-axis end up being positive and areas below the x-axis end up being negative. So just to indicate that, this area here would be positive in our calculation, which again we'll see in a little bit. That area would be positive, this area would be negative. So it's like this net area or signed area. And we sort of saw this with Riemann sums, even though we weren't doing actual definite integral calculations yet, where we had the positive area cancel out with the negative area for that sine of x function. It's the same thing with definite integrals, this sort of more precise version of area calculation, if our function dips below the x-axis on a given interval of interest. So just some things, and we'll see a lot more with this in the next several sets of notes. So we're not going to really get into this difference yet, but we will see it a little bit later. So the next things I want to do, this first one is I want to use that limit definition of the definite integral, taking the limit of that Riemann sum, to show that we get an exact area using the definite integral definition. So that's what we're going to do here with a pretty simple function. I've got a picture of it here, just a rectangle. And then what I want to do is I want to do just a couple examples where we're considering, again, that relationship between the definite integral and area. So we're not actually going to be calculating the definite integral itself the way that we'll be doing later with actual calculus. But I want to link this notation with this idea of area before we start actually doing calculations with it, because I think remembering that when we're calculating a definite integral, we're actually calculating an area makes the definite integral a little bit easier to understand and work with. So again, we're not really doing any calculus, at least for these examples, any integration. We'll get to that later. But this is more just to emphasize that relationship between the definite integral and area beneath the curve. So we'll get to that in a second. But what I want to start with here is I want to start by looking at how we can compute area using the limit definition of the definite integral, which comes from our Riemann sum definition. So our function here is f of x equals 3, and we want to use the limit definition of the definite integral to find the area under the graph, so under this function's curve, from x equals 0 to x equals 4. So at the bottom of this page, I just have a picture of this function and the area we're looking at. It's pretty boring, but it's useful for this example. Here's our function. If our function is just a constant, like it is here, then it just gives us a horizontal line at that constant. And our interval here is from 0 to 4, so this shaded area is what we're looking for. Now, the reason I'm picking this function in this particular area is because this is just a rectangle, which we've seen already. We can calculate the exact area using an area formula. But I want to back that up, or I want to use that to back up the answer we get by using that limit definition that we introduced a couple pages ago. So let's write down the limit definition and then see what we can do with it. So the limit definition of the integral, of the definite integral, what I mean by that is this. So this is the definite integral, but as a limit definition. So it's a limit of that Riemann sum. So let me write this down and then let's fill in what we know. So the limit definition of the definite integral is the limit as n goes to infinity of the sum from I equals 1 to n of f of x sub I star times delta x, which this is that b minus a over n, so it's that width. So we'll fill that in a second, but let me just label it here. So this is, just like we were seeing in the previous set of notes, the definition of our Riemann sum. It's the sum of our rectangle's widths times their heights. In other words, it's the sum of our rectangle's areas. So just like we were doing with the Riemann sum, I'm going to go ahead and ignore some of this. I'm going to ignore the limit, I'm going to ignore the sum, and I'm just going to think about the width and the height for this particular function, f of x equals 3. So let's start with the width. So the width is delta x, and we saw that we could calculate this by taking b minus a over n. So what's our n here? Well, n, we don't have a specific number of rectangles we're using here. We're just saying we're using n intervals of equal width. So our n, I'm just going to keep it as n. I'm not going to plug in a value for it. A and b, though, a is 0 and b is 4. Those are the endpoints of the interval of interest. So my width, I'm going to define as b minus a, 4 minus 0, over n, which is just 4 over n. So n is just standing in for some arbitrary number of intervals, arbitrary number of rectangles. So that takes care of the width. That's the same width for each rectangle. What about the height? So for most functions, the height's going to be different from x to x, because most functions, as we saw with Riemann sums, those examples, they have some sort of curvature to them. But when we talk about this particular function, f of x equals 3, and we can see this from the graph, no matter what x I choose, the height is always going to be 3. So no matter what x value I choose to assess the height of my rectangles, the height is always going to be 3 just by virtue of this particular function. So my height is always going to be 3. So this is going to be 3 for any value of f of x sub I, for any value of x sub I star. It just means that my height doesn't really have a calculation to it. It's just always going to be 3, again, by virtue of this function. It's just a constant, so the height is going to be constant at 3. All right, so now let's stop ignoring these pieces and see what we can do. So we're going to take the limit, we're going to take the limit as n goes to infinity of the sum from I equals 1 to n of my heights, which we just said was 3, times the widths, which we just said was 4 over n. Now, this is not something we're going to ask you guys to do on a final or anything like that, or for any of the assignments. This is just a demonstration. So some of this stuff might be a little bit beyond what you may have learned in other math courses. That's okay. Again, this is just a demonstration, just to show you that this limit definition works. We're going to be using other ways of actually computing definite integrals later. But some of this stuff, if you've never seen it before, that's okay. Don't worry too much about it. It's just, again, showing why this process works. We're not going to ask you to do this sort of thing anywhere else other than here. So don't worry about that. Okay, so what am I going to do with this? So I'm taking a limit of a sum. That seems kind of weird. So let's see if I can simplify the sum a little bit. So I've got 4 over n. that's just going to be I can think of that as just a number involving n. So what I'm going to try to do is I'm just going to take that out of my sum. And I can do that because all of my rectangles are going to have the same width. So I'm going to go ahead and take the width out of the sum and write this as the limit as n goes to infinity of 4 over n times the sum from I equals 1 to n of 3. Now I still have a sum in my limit calculation, which is a little bit weird. So is there a way that I can simplify this? Well, I'm taking the sum of a constant, 3, and I'm summing it n times. So what does that mean? Well, if I think about, let's say, the sum from I equals 1 to 2, that means I'm summing 2 3's. So this would be 3 plus 3. Or 2 times 3. If I'm summing from I equals 1 to 4, 3's, that's going to be 3 plus 3 plus 3 plus 3, which is 4 times 3. If I'm summing from I equals 1 to 12, 3's, that's going to be 3 plus 3 plus all the way up to 12 3's, which is 12 times 3. And so if notice that these are all matching this product here. It's the upper sum value times the thing we're summing, 3. And so if my upper value here is n, that means I'm summing 3 n times, which would give me n times 3, or that's usually just written 3n. So I can actually get rid of the sum by knowing that this thing is equal to 3n. And again, I'm just kind of showing that with a couple examples here. And this is part of the thing that maybe you've seen this before in other math courses, maybe not. Again, if you haven't, don't worry too much about it. Just for now, think of the sum from I equals 1 to n of 3 as 3 times that n, which means our limit is now the limit as n goes to infinity of 4 over n times 3n. And I can see at this point that the n's cancel each other out, which means this is going to be the limit as n goes to infinity of just 4 times 3, which there's not even an n in there, so I don't even have to worry about n going to infinity. 4 times 3 is just 12. And so what this 12 is, just to kind of link this to what we're going to be doing later, this is the definite integral of this function from 0 to 4. It is the exact area under the function from 0 to 4. So another way that I could express this is the integral from 0 to 4 of 3. So I'll kind of put a little cloud around that because this is the idea. What we just did is we used the limit definition of the definite integral to get to 12. And here I'm just indicating that another way that we could express that is as the definite integral of 3, the function, from 0 to 4. And this is why I chose this function. This is something that's easy to verify because the picture is just a rectangle. So if I want to verify this using geometry, I can remember that the area of a rectangle is the length times the width. So if we let the 0 to 4 be our width and the height be our length, that's going to be length, which is 3, times width, which is 4, which gives us that area of 12. Now, another reason that I did this, not just to kind of demonstrate how this limit definition works, but also to demonstrate that if we have a function where the heights aren't constant, this might get a little bit more complicated or convoluted when we're trying to use the limit definition of the definite integral. Here, I chose a pretty easy function where the height was also constant, so we didn't have to worry too much about determining the function of the height based on the rectangle that we're using. But if we had a more complicated function, this limit calculation would get more difficult and less easy to work with. And I'm pointing that out because what we're going to see in the next set of notes is we're going to see how to do this sort of thing, this sort of calculation, without having to use the limit definition. So the limit definition basically is going to be working in the background for us. But what we're going to see in the unit or the topic 11 notes is we're going to see the evaluation theorem, which gives us a nice shortcut for definite integrals where we don't have to explicitly take any limits. And it's going to be really nice, and it's going to be really fast, and it's going to be so much better than taking limits, even a limit that's not super complicated like this one. So kind of giving you a preview of what we're going to avoid once we get to topic 11 with the evaluation theorem or the evaluation process. So this is how we would compute the exact area using the limit definition of the definite integral. Again, this is like the last time we're going to see it because we're going to have something that makes this better and faster and doable without limits. So that's one of the examples I wanted to do. The other two examples are really to emphasize again this relationship between the definite integral and area. So I've kind of mentioned here the usefulness of that evaluation theorem that we're going to see later. For these next two examples, again, I'm just trying to emphasize that relationship between this new concept, the definite integral, and area. So we're going to be seeing the notation, at least here, for a definite integral, but we're going to see that we can figure this out by area. And later, in one of our later examples, we're going to do the same thing again, but use the evaluation theorem and see that we get the same thing. So just making that link between area and the definite integral. So let's take a look at this example. So here, we are trying to find the definite integral of the absolute value of x from -2 to 3. In other words, what we're doing with this is we're finding the exact area beneath the curve defined by the absolute value of x on the interval -2 to 3, which is shaded in this picture. Now, like I mentioned, in topic 11, we're going to learn how to do this using the evaluation theorem, where we just use calculus. But for now, we're just emphasizing that this can be thought of as just a bunch of area calculations, or specifically 2 area calculations. So what I'm going to do is I'm going to take these 2 pieces and notice that they both look like triangles. Like this thing looks like a triangle. I'll label this piece A, and this thing looks like a triangle. I'll label this piece B. And so to emphasize that relationship between the definite integral and area, I can think of this definite integral from -2 to 3 of the absolute value of x being the area of triangle A plus the area of triangle B. So it literally is just the area defined by these 2 shapes, which for this purpose, they're easy workable shapes in terms of area calculations. So we're just going to do this using geometry. So remember, the area of a triangle is 1/2 times its base times its height. So if we look at the area of A, we can see that its base looks like it is 2 units. So from 0 to -1, -1 to -2, and its height also looks like it's 2 units. So the area of A is going to be 1/2 times the base times the height. And then for B, we can see that it looks like its base is 1, 2, 3 units, and its height is also 3 units. So for B, our area is going to be 1/2 times 3 times 3. And so that's going to give us, for the red triangle A, that's going to give us an area of 2. And the purple triangle B, that's going to give us an area of 3 times 3 is 9 times 1/2 is 9/2. So we can say that's 4/2. 2 can be expressed as 4/2 plus 9/2, which is 13/2. And again, this thing is the definite integral, the exact area, from -2 to 3 of the absolute value of x. And we're just doing it this way because here we have an easy enough structure to our function where we can do this geometrically. But I'm doing it to emphasize, again, that relationship between the area and this notation for the definite integral. Okay, so let's do one more and then talk briefly about some properties of definite integrals, which we'll see in practice in a little bit instead of in this set of notes. But let's consider this function. So this function is just called f of x, and we want to find the definite integral from 0 to 13 of this function. In other words, we want to find the exact area under the curve of this function from 0 to 13. So here's 0, 13 is right here. So just to mark those in so it's a little bit easier to see. And so when we talk about the area, or the definite integral, it's going to refer to the area beneath this curve above the x-axis and the area beneath the x-axis and this curve. So I'm integrating from 0 to 13, f of x. And again, I'm not using any calculus yet. I'm just linking this to this idea of area, net area. And what I'm going to do is I'm going to see if I can break up this weird-looking region into easy-to-work with pieces or forms where I know the area calculations. So let's see what we've got. If I look at this piece here, so I'm going to use a couple different colors here. I'll use red for the first one. This first piece looks like it's a triangle, which is a nice, easy shape to work with because we know its area calculation. We know its area formula. I'm going to call that A. If I look at this little piece here in the middle, this looks like a rectangle. Another easy to work with shape. So I'm going to call this B. It looks like we have another triangle right here. I'll call that C. And then finally, if we go below the x-axis here from 13, it looks like this piece is also a triangle. I'll call this D. Now I also included this example to emphasize that idea of net area when we've got a function that dips below the x-axis. So when I compute the area here, which again is the same thing as this definite integral from 0 to 13, the way I'm going to compute this is I'm going to calculate the area of A plus the area of B. I'm just using the letters, but I'm going to calculate the areas for these letters, plus the area for C. And then I'm actually going to subtract the area for D because D, that region, is all below the x-axis, which means in terms of signed area or net area, it's going to be negative. So for my area calculation, aka my definite integral calculation from 0 to 13, this is the way I'm going to think of it. So just to have our formulas up here, area of a triangle, that's 1/2 times the base times the height, as we've seen. And area of a rectangle, that's going to be length times width. So let's take a look at what we've got. So let's start with A. A is a triangle. So its area is going to be 1/2 times its base. Its base goes from 0 to 6, so its base is 6. And its height goes from 0 to 6, so its height is also 6. B is a rectangle, so we can look at its length times width. Let's say its length is its height, that's 6, and its width is 2. So the area for B is going to be 6 times 2. Plus the area for C. C is another triangle, so its area is going to be 1/2 times its base. Its base looks like it's 2 units, and its height looks like it's another 6 units. So 1/2 times 2 times 6. And then I'm going to subtract from that the area for D, again because D is below the x-axis. D is another triangle, so that's going to be 1/2 times its base, which is 1, 2, 3, times its height, which looks like it goes down to 9. So that gives us, let's see, 1/2 times 36, that is 18, the area for A, plus 6 times 2 is 12, the area for B, plus 2 times 6 is 12, times 1/2 is 6 for C. And then we're subtracting the area for D. 3 times 9 is 27, divided by 1/2. I'll just write that as 27 halves. +18 plus 12 plus 6 is 36, minus 27 halves. To get a common denominator, 36 in terms of halves is 72 halves, minus 27 halves. So 72 minus 27 gives us 45. So this area is going to be 45 halves. Or, in other words, the definite integral, the net or signed area between 0 and 13 for this particular function is 45 halves. So like I mentioned, we're going to see some more rigorous calculations of that using actual calculus, actual integral calculations a little bit later in the topic 11 notes. Now, one other thing I just want to mention here really quick are a couple properties of definite integrals. Now that we kind of know this relationship between definite integrals and area, we have some properties that can help us sort of keep in mind what happens to a definite integral depending on what we're doing to it or how we're integrating or things like that. So I'm not going to go over these in too much detail just because we'll see them in practice in the next couple sets of notes and they'll make more sense there. But just to mention a couple of these and draw some pictures for some of them as well. If we are taking the definite integral of a function times a constant c, we've seen this with a lot of different things. If we have a constant, we can take that out of the integral and multiply the integral of f of x by the constant. So that one's not really new. We've seen that sort of property with derivatives, and we saw it with limits as well. This second one can be useful in the sense that if you have maybe a picture of a function and it looks like it can be broken into two different pieces by a sum or a difference, we can integrate the sum or the difference of the functions by taking the sum or the difference of the integrals of the functions. So I have space to draw this here. I don't think I'm going to draw anything specifically. I might close that space because this is something that I think is easier to see with the actual functions rather than drawing a picture. But the idea is if you have two functions that are either being added or subtracted within an integrand, you can break up the integral calculation as the sum or the difference of the integrals of the specific pieces of the function. Number 3, though, this is one I am going to draw. If we are integrating where our limits of integration are the same, then the result is going to be 0. And that again comes down to this idea of area. So if I have a function from a to b, actually let me use different values here because I have a up there. Let's use c to b. And let's say my function, I don't know, is doing this. If I have a point A and I'm integrating from A to A, what that means is I'm just looking at the area defined right here, this line. And when we think about a line, there's not that second dimension to give us any area. It's just a straight line. And so there's no area between A and A. It's just a straight line, no actual two dimensions. So that's why if we integrate something from A to A, 6 to 6, 18 to 18, negative 400 to negative 400, the result will be 0. There's no area between the two same points. This is one that is more of a useful thing to rewrite integrals, which we're going to see a little bit in the topic 11 notes when we look at the first part of the fundamental theorem of calculus. If I'm integrating a function from a to b, that's going to be equivalent to integrating the function from b to a and negating the result. So this is a little bit of a weird one, but it is a useful one, which we're going to see at the start of topic 11. So I'm not going to do too much with it because it doesn't really do much for us outside of topic 11 and outside of the application of the first part of the fundamental theorem of calculus, but it is useful, so I wanted to put it in this list. One that can be really useful visually, and especially if you have complicated functions or improper integrals, which we're going to talk about almost at the very end of the semester, is this fifth property here. So let me start by drawing a picture. Let's say we have, here's A, here's B, and here's C. And let's say our function is doing something like this. If we want the integral from A to C, so in other words, if we want to figure out the area beneath the curve from A all the way down to C, if we are able to split that integral into two neighboring pieces with a common limit, let's call it b, then I can actually split this integral into two separate integrals. So what do I mean by that? Well, if I have b right here in the middle, and if I integrate from a to b, that gives me this area. And if my other integral here is the integral from b to c, that's this area, then if b is that common limit of integration, I can actually sum these two regions, these two areas, to get the overall area from A to C. So it's like I can bypass that b because it is this common limit of integration. And so if I'm integrating from A to B and then from B to C, I can just sum those two pieces to get the integral from all the way from A to C. So We'll see the usefulness of that when we talk about improper integrals, or integrals where we've got infinity signs somewhere involved in the situation, because sometimes it helps to break up the structure of our integral by some arbitrary middle point or some arbitrary point in between a and c to make our actual calculations easier and doable. So we'll see this particular useful function or useful property in topic 12 when we get to improper integrals. So what we're going to do in topic 11 is we're actually going to learn a couple rules for calculating definite integrals without having to do limits, without having to deal with geometry. We're going to finally do the actual calculus part of taking a definite integral. So we'll see that in topic 11.